Welcome to this week's first lecture in EE557. In the last lectures, we have seen the Bayesian recursion and its application to Markov chains. In this lecture, we are going to see the application of Bayesian recursion into linear Gaussian systems. So let us first remember the Bayesian recursion. In that case, we have P0 given -1 of x0 is equal to P of x0. This is the initialization step of the Bayesian recursion for estimating the posterior density of the state given all of the measurements. And we have then the measurement update. We have Pk given k of xk is equal to the likelihood Pyk given xk times Pk given k minus 1 of xk divided by the normalization constant of this multiplication. dxk. Okay? And finally, we have the time update, which is Pk plus 1 given k of xk plus 1 is equal to, this is an integral only, and I have Pxk plus 1 given xk and uk, and Pk given k, xk, and the integral is again with respect to xk. In the last lecture, we have seen the application of these equations into Markov chains, where the densities became just vectors, and we have seen the counterparts of these equations in the case of Markov chains, which were just matrix vector multiplications and the summations, of course. So now let us try to apply these into linear Gaussian systems. So estimation for linear Gaussian systems. In this case, I will start first by writing the system equations. So I would have xk plus 1 is equal to, I have axk plus buk plus gwk, and wk is the process noise here. And we know that wk is distributed as normal with zero mean and covariance q. Here I make the system time invariant, but in general, of course, this a, b, g can depend on time. So I can write a sub k, b sub k here. But here we are going to consider the time invariant case for the sake of simplicity. And I would have yk is equal to cxk plus hvk. And vk is my measurement noise. It's normal with zero mean and covariance r. And also I need to define here what x0 is. x0 is random, which is normal distributed, with mean x0 bar and covariance sigma 0. Okay? And then I need to talk about the input. uk is either deterministic or uk is equal to gk of y of 0k. Okay? One of which represents the open loop case, and the other one represents the closed loop case. And of course, we have the common assumption here, x0, w0, w1, v0, v1, going until infinity are independent. Okay? So this is our system, and our aim is going to be to calculate the posterior distributions of the state. So I need to calculate pxk given y0k. But remember that we calculate this posterior distribution using a recursion in two steps. First, the measurement update, and then the time update. So in general, we're going to calculate two distributions here. This is the estimated posterior distribution, and I would have or filtered posterior distribution, and this is the predicted posterior distribution. We're going to calculate both of them here. And since the system is linear Gaussian, we know that all variables here, all variables in this system, they are jointly Gaussian, okay? So these posterior distributions are also Gaussian distributions. So I know that this Pxk given y0k is a Gaussian distribution, which means I'm going to call it xk given k hat, and the covariance sigma k given k. And this distribution is again going to be a Gaussian distribution, which it is a Gaussian distribution for the random vector xk plus 1, and I will call its mean as xk plus 1 given k hat and sigma k plus 1 given k. Okay? And here, what are these xk hats and these sigmas here? If I write their definition, then I would have xk given k is nothing but expected value of xk given all of the measurements, and x at k given, k plus 1 given k is equal to expected value of xk plus 1 given all of the measurements between 0 and k. Okay? And if I define the covariances, of course, sigma k given k is nothing but the covariance of xk given y0k, and sigma k plus 1 given k, these are all definitions. It is xk plus 1 given y0k. Okay? And here I can actually write the definitions here, the definitions of these covariances, expected value xk minus x at k given k here. And I will multiply the same quantity transpose. Sometimes, in order to save time and effort here, instead of writing the outer product completely like this, I will write something in parentheses and an empty parenthesis here, and transpose. This is going to mean that xk minus x at k given k times xk minus x at k given k transpose given y0k. This is a definition of this sigma k given k in terms of the expected values. And I would have here xk plus 1 minus x at k plus 1 given k. And I would have the same thing transposed here. And of course, I have the given condition, y0k. Okay? So now we know that we are obtaining posterior distributions by applying such a recursion. So where do we start this recursion? For example, I can have P of xk given y0k minus 1. This is the predicted distribution in the previous step. Then I apply it something called a measurement update or a correction, and yk enters into this correction, and I calculate pxk given y0k here. Sorry. This is the filtered distribution, and then I make another time update to calculate the next predicted distribution. So this is our recursion, and I then have a z minus 1 here, and then I connect this side to the other one. So we have a recursion updating, calculating these distributions in an iterative manner. So now I have learned that these densities are Gaussian, so really I do not have to deal with functions anymore, okay? I do not have to deal with functions of xk or xk plus 1. So in order to be able to store and process these distributions, all I have to do is to keep track of their mean and their covariance, okay? So this one has a mean and covariance. That mean is xk given k minus 1, and the covariance is sigma k given k minus 1. Then I need to update this mean and covariance using the measurement yk to obtain the mean and the covariance x at k given k and sigma k given k. And then I need to apply time update to this mean and covariance to obtain x at k plus 1 given k and sigma k plus 1 given k. Okay? So really here I do not have to deal with this, the infinite dimensional quantities here. All I need to deal with is the mean and the covariance of those distributions. So knowing that our densities are Gaussian reduces the infinite dimensional Bayesian recursion problem into a finite dimensional estimation problem where we need to calculate only mean and the covariances, calculate and update. Let us start with the initialization step of our Bayesian recursion. So we know that here P0 given -1 of x0 is going to be P of x0. Okay? I know that this is a Gaussian distribution now. So I have normal x0 given -1 and sigma 0 given -1. Remember that given -1 means that we're given nothing, okay? So this has to be equal to the P of x0, which is this distribution here, okay? So I need to equate these to these Gaussian distributions. And this makes x0 bar and sigma 0. So this means that here, in order to be able to make the initialization of the Bayesian recursion for a linear Gaussian system, all I have to do is to equate the initial mean to the initial mean of the state x0 and the covariances here. So the initialization step is nothing but equating x0 given -1 to x0 bar. Nothing is given. I just look at the mean of x0 when no measurement is given. And finally, we have sigma 0 given -1 is equal to the initial covariance of the state x0. Okay? So this is my initialization step. Now let us go into the measurement update step. Because the next step is going to be updating this predicted mean and covariance using y0. That means that we are going to have to do the measurement update in the next step, and that is what we are going to derive here. So this was the initialization. And now we are considering measurement update. Measurement update is this formula here, okay? And I know all of these distributions. Let me calculate the likelihood for this linear Gaussian system. Pyk given xk, the likelihood for our problem is nothing but, again, a normal distribution, normal yk, and when xk is given, its mean is cxk, and its covariance is the covariance of the remaining term, hrh transpose. So this is my likelihood for this problem. And now what I have to do is I can actually substitute it into this formula. So pk given k is a normal distribution, normal xk, x at k given k, sigma k given k, is equal to, the likelihood is given by this, normal yk, cxk, hrh transpose, times the predicted distribution, normal xk, x at k given k minus 1, sigma k given k minus 1, divided by this quantity integrated, okay? dxk, okay? So we get such a nice formula for the distributions. So we see that here the Gaussians are multiplied and they are integrated and divided, and we have a division here. So then what we have to do is actually to calculate this mean and covariance in terms of this mean and covariance and the measurement parameters here, y, c, and hr, h transpose. Okay? So when we look at this integral, we can actually expand these Gaussian terms into their explicit formulas, and then we can try to manipulate those exponentials and square root determinants, and we can calculate here what this x at k given k and sigma k given k would be in terms of the other quantities. But here we are not going to follow that approach. That is a way of deriving this measurement update. Actually, deriving the update from the predicted quantities into the updated quantities can be made in many ways. I actually know at least 3 ways of deriving these equations, okay? And this is using these normal distributions and expanding them, and then making algebraic manipulations and taking these integrals is a way of doing doing that, or calculating those measurement update formulas. But here we are not going to follow that approach. We are going to choose another approach that we are familiar with in this course. Actually, we have been using that approach from the start of the semester continuously. So here is what we are going to do. We are going to use the conditional Gaussian update formulas in order to be able to calculate the update formula for these mean and covariance from these mean and covariance and the measurement quantities. So I'm stopping this approach here. Instead, I'm going to use an easier approach that we are familiar with. And actually, I told you that I know multiple ways of deriving these update formulas, and usually the easiest one is the one that we are going to be using. So now we know that xk given y0 k minus 1 is distributed as follows. This is my predicted distribution, okay? And that is xk, x at k given k minus 1, and I would have here sigma k given k minus 1. Okay? So this is my distribution, and in the measurement update I need to calculate the distribution of this quantity. Okay? xk given y0k. So I need to incorporate yk into the conditioning here. Okay? But what is this? xk given y0k is nothing but yk and y0k. Okay? So I can divide this y0k quantity into two parts. The first part is yk, and the second part is y0 to k minus 1. Okay? So you see that here in both of these parts I have the common conditioning y0 given k minus 1. Okay? So the only thing that I need to do is that I need to bring into conditioning a new variable that is yk. Okay? So in order to be able to do that, we are actually going to be using the conditional Gaussian update formulas. Okay? So we know actually when we have the variable xk and yk jointly Gaussian distributed, we know how to calculate xk given yk here. Okay? Here the only difference to that is that we have an additional conditioning of y0 k minus 1 in both of the quantities. Okay? So I need to calculate here normal xk, x at k given k, and sigma k given k. Okay? So I need to derive from this mean and covariance and this measurement, this mean and covariance here. And we are going to use the common conditional Gaussian update formulas in order to be able to do that. So now let us look at yk. Yk here is cxk plus hvk. Okay? Suppose that we are given y0 k minus 1 here. Okay? I know that when I look at yk is composed of two parts, cxk and hvk. All right? I know how cxk term is distributed because given y0k minus 1, xk is distributed by this predicted normal distribution. Okay? And I know the distribution of hvk, and furthermore, I know that vk is independent of all of the previous measurements and the states. Okay? Vk is independent of all of the previous measurements and the states. Okay? So here, this given condition has no effect on the distribution of hvk. Okay? So I know that this term is Gaussian with some mean and covariance given y0k minus 1. And I know that this term is Gaussian and the given condition does not affect it. Okay? Vk distribution is this one, and I can know the distribution of this one. So I have the summation of two independent Gaussian distributions two independent Gaussian random vectors here. Okay? And how do I know that they are independent? Because given y0k minus 1, I know that this hvk is independent of the previous states and independent of the previous measurements. Okay? So here, given this y0k minus 1, cxk and hvk are actually independent from each other. And I know that these are Gaussian given y0k minus 1. Because xk is Gaussian, therefore cxk is going to be Gaussian. And furthermore here, this hvk is Gaussian because vk is distributed like this, and vk is independent of y0k minus 1. Okay? So yk is nothing but the summation of two independent Gaussian random vectors, okay, given y0k minus 1. That means that yk and xk, given y0k minus 1, they are jointly Gaussian. Okay? So this is the important point here. We know that given y0k minus 1, yk and xk, they are jointly Gaussian. Okay? And actually, this is not a magical result, or this is not a surprising result, because in linear Gaussian systems, all variables are jointly Gaussian with each other. Okay? So actually here, for a linear Gaussian system, the system is linear, the noises are all Gaussian, I have the independence, and I have this Gaussian initial condition. All joint distributions are also Gaussian distributions. And all joint posterior distributions are Gaussian distributions. Okay? But here, for this specific case, we have xk and yk are jointly Gaussian given y0k minus 1. So here then why not write the joint distribution? So I can here write the distribution of xk and yk given y0k minus 1 as a normal distribution of xk and yk, joint normal distribution. Okay? And I will have a mean, I will have the means here, and I will have the covariances here. Okay? Let us try to fill in what we know so far about these distributions. I have xk here. This quantity is going to be the mean of xk given y0k minus 1. Okay? Mean of xk given y0k minus 1 is this mean. So I have here x set k given k minus 1. And here I need to have the marginal covariance of xk given y0k minus 1. And that is nothing but sigma k given k minus 1. Okay? And what about the rest? These are the known quantities now. Currently, I don't know what the mean of yk is, given y0k minus 1. And I don't know these covariances either. But I know that this covariance matrix should be symmetric. Okay? So that is a good thing. Therefore, I don't know only 3 quantities. This mean, this covariance, that is cross covariance, and the marginal covariance of yk given y0k minus 1. Let us start giving some names here. I would call this sigma k given k minus 1, and I would put here an xy, okay? And here I would write k given k minus 1 y, and here I would write y hat k given k minus 1, and this part is going to be just the transpose of this matrix, okay? K given k minus 1 xy transpose. So which ones are unknown here? I know in the measurement update, I know the predicted quantities. I know this one and this one. So this is not known, this is not known, and this is not known. All right? Let us now try to calculate those unknown quantities. Then what then? What is going to happen afterwards? Then I need to calculate what is xk given yk. But here you see that y0k minus 1 is already in the given conditioning. So as soon as I pass this yk into the conditioning, I will calculate xk, the statistics of xk given yk and y0k minus 1. Okay? But when they're combined, they're going to make y0k. Okay? So that is all we are going to do here. So we are going to calculate this joint Gaussian distribution parameters, and then we are going to use the conditional Gaussian mean and the covariance formulas for calculating this x set k given k and sigma k given k in terms of these predicted quantities plus the measurement here. Okay? So now the first task, but is going to be to calculate these unknown quantities. Okay? So the first thing that we are going to calculate is going to be this. Y hat k given k minus 1. The first unknown quantity. This is nothing but expected value of yk given y0 k minus 1. Okay? The expected value that I put here is going to be the marginal mean of the variable yk given y0 k minus 1. Okay? That is going to be expected value. Yk is given like this, cxk hvk given y0k minus 1. All right? Now I know that expectation is a linear operation, so I can distribute it into multiplications and the summation. So that is going to be C expected value xk given y0k minus 1 plus H expected value vk given y0k minus 1. Okay? Now, what is the first quantity? C times expected value xk given y0k minus 1. I know that this is nothing but x hat k given k minus 1 plus h times, I need to calculate this expectation. I know that vk is independent of y0k. So that means that this expectation, I can remove this conditioning from here. That's going to give me expected value of vk. But expected value of vk is 0. Okay? So as a result, there is no summation here. I need to add just 0, but we don't need to do that. So the first unknown quantity, the predicted measurement, yk given k minus 1, the predicted value of the measurement at time k, given all of the past measurements, is c times predicted value of the state. Okay? So here, from this equation, we see that if I multiply the predicted value of the state with C, and because the expected value of Vk is equal to 0, we have this predicted measurement. Okay? Now let us go into the second unknown quantity. I will choose this one now, sigma k given k minus 1y. Sigma k given k minus 1y, this is nothing but the marginal covariance of y given y0 k minus 1. Okay? So this is covariance of yk given y0 k minus 1. Okay? But I can write it as formula, expected value of yk minus y hat k given k minus 1 times the same quantity transposed. Okay? Of course, I need to write the given condition here. Given y0 k minus 1. Okay? So now I'm ready to actually do this subtraction. So yk minus y hat k given k minus 1. This is nothing but I would have here this cxk plus hvk minus y hat k given k minus 1 is cx hat k given k minus 1. Okay? So that means that I would have c xk minus x hat k given k minus 1 here, okay, plus h vk. And I need to take the outer product of this quantity. So what does that mean? This sigma k given k minus 1y is going to be this expected value of this quantity cxk minus x at k given k minus 1 plus hvk times the same quantity transposed. Okay? I'm always forgetting the given condition here. It's unforgivable here. Okay? I cannot forget, I shouldn't forget those given conditions. So now let us try to, so the thing that here is that these two quantities are independent, okay? Because Vk is independent all of the states and the previous measurements, and it's also independent of xk as well. All right? So here, actually, I can calculate the covariance of this quantity given y0 k minus 1 and the covariance of this quantity, and then I can sum. Okay? But here, just to show you what the calculation looks like here, I'm going to distribute this outer product. Okay? So that is going to be expected value C xk minus x at k given k minus 1 times its transpose here. Xk minus x at k given k minus 1 transpose times C transpose. Okay? And I have, of course, y0 give to k minus 1. Okay? This is the first term in the expansion of this outer product. Okay? And then I have expected value of, I would have cxk minus x at k given k minus 1 times vk transpose h transpose. Okay? And of course I have the given condition y0 to k minus 1. Okay? The next term is going to be the transpose of that plus expected value. I have h vk times I would have xk minus x at k given k minus 1 transpose times C transpose plus the last term, multiplication of this one with this transpose. Given y0 k minus 1, and I would have expected value of h vk, vk transpose, h transpose given y0 k minus 1. So now let us look at this quantity here. Expectation of C and C transpose, these can go outside the expectation because these are deterministic, they can get outside the expectation. And then I need to calculate expected value of this quantity given y0 k minus 1. But that is nothing but my covariance sigma k given k minus 1. This covariance, okay? And what about this expectation? I know that Vk and xk minus x at k given k minus 1, they are independent, okay? So that means that I can actually take the expectation of this quantity given y0 k minus 1 and take the expectation of Vk transpose given y0 k minus 1, and both of them are going to be equal to 0, so this cross product, the expectation of this cross product is going to be equal to 0. Okay? Similar for its transpose as well. And what about this? I have expected value of H transpose here. These can go out because they are deterministic. And I need to calculate expected value of Vk transpose given y0 k minus 1. This given condition y0 k minus 1, it means nothing here because the only randomness is coming from Vk and Vk is independent with y0 k minus 1. So here all I have to do is to write H and H transpose, and in the middle I need to write expected value Vk transpose. And in that case we know that that is going to be the covariance of Vk, which is R. Okay? So now I can write the final formula here. And I can erase this one as well. So this is going to be C times, I know that this quantity expectation given y0 k minus 1 is Ck given k minus 1, C transpose, plus I have 0 expected values, and I have here HR, H transpose. Okay, so this is my second unknown. All right. Let us calculate the final unknown quantity. And that's going to be just this cross covariance. So sigma k given k minus 1 xy, it is by definition just this one. So I would have here xk minus x at k given k minus 1. Maybe I should write first in the covariance notation. So this is covariance of xk with yk given y0 k minus 1. All right? And we know that this is nothing but expected value of xk minus x at k given k minus 1 times yk minus y hat k given k minus 1 transpose given y0 k minus 1. All right? Now that is equal to expected value of xk minus x at k given k minus 1 times, we have already calculated this quantity. What was it? C times xk minus x at k given k minus 1 plus hvk. Okay? Given y0 k minus 1. All right? Now I have to take the transpose of the second term, we'll multiply this with this one, and then take expectation given y0 k minus 1. Okay? So now let us try to do it. The first thing that you need to realize here is that this multiplication of hvk with this xk minus x at k given k minus 1, that expectation given y0 k minus 1 is going to be 0 again. Okay? So the only expectation remaining is going to be the expectation of this term times C transpose. And you know what it is going to give you. This term times its transpose expectation given y0 k minus 1 is sigma k given k minus 1 times C transpose. Okay? So our third unknown quantity is just going to be this one. This is the cross correlation of xk and yk given y0 k minus 1. So it should be sigma k given k minus 1 times C transpose. Okay? And this is our third unknown quantity, the final unknown quantity. Now I know what are these unknown terms. Okay? Now all I have to do is to calculate expectation of xk given y0k. So I need to assume that this yk is given to us, and I need to calculate the conditional expectation of xk given yk. And here, these previous measurements, they are already given to us, and we calculated these statistics here, assuming that those given conditions were already there. Okay? So this expectation, this is nothing but x hat k given k. And what I am doing is nothing but taking this yk to the given condition. Here we are just going to use our classical Gaussian update conditional Gaussian update formulas, or conditional Gaussian mean and covariance formulas for this Gaussian distribution. Okay? So now what is this going to be? Do you need, let me write those. So what was the formula? So I have x and y. When I have a Gaussian distribution of x and y here, when I have the mean x bar, y bar, and the covariance is sigma x, sigma y, sigma xy, sigma xy transpose, in that case I know that expected value of x given y happens to be x bar plus sigma xy, sigma y inverse times y minus y bar, okay? And covariance of x given y is nothing but sigma x minus sigma xy, sigma y inverse, sigma xy transpose. These are our formulas, and that is what we have to just apply here. Okay? So now x at k given k is nothing but taking this yk into the given condition of this Gaussian distribution. And that is going to be first the mean of x. Okay? Mean of x is here is x at k given k minus 1. All right? Plus the cross covariance, sigma xy. This cross covariance is just this one. Sigma k given k minus 1 xy. And the marginal covariance of the measurement inverse, sigma y inverse. So sigma k given k minus 1 y inverse times the measurement y. The measurement here is yk minus its marginal mean, y hat k given k minus 1. So this is our update formula, updating x at k given k minus 1 into x at k given k using the measurement yk. Okay? And what about sigma k given k? This is going to be the covariance of xk given y0k. I would use the covariance update formula, or conditional covariance formula in that case. It's going to be the marginal x covariance, sigma k given k minus 1, minus sigma k given k minus 1 xy, sigma k given k minus 1 y inverse times sigma k given k minus 1 xy transpose. Okay? So we would have this update formula. Now I can get rid of this joint Gaussian, and we can go into the explicit formulas when I replace these covariances with their equivalent expressions here. Okay? So now let me write the update formula. X at k given k is equal to x at k given k minus 1. The updated mean is the predicted mean plus some quantity here, sigma k given k minus 1 xy, and it is this thing, sigma k given k minus 1 C transpose, times this covariance inverse, so this thing inverse here, C sigma k given k minus 1 C transpose plus HR H transpose inverse times yk minus y hat k given k minus 1. It is C times x hat k given k minus 1. Okay? And I have sigma k given k is equal to the filtered covariance is the predicted covariance minus. So here, this is my predicted covariance. After I get this measurement yk, I am subtracting some matrix from this covariance. So the covariance gets smaller in this update. Why is that? Because we are collecting a measurement or information about the state in the measurement. That means that the uncertainty of the state should get smaller. Okay? And this subtraction just means that we are making the predicted covariance smaller in the filtered covariance. Okay? That is sigma k given k minus 1 minus, I would have the same term, sigma k given k minus 1 C transpose times this thing inverse again, sigma k given k minus 1 C transpose plus HR H transpose inverse times the covariance of the same thing, C sigma k given k minus 1. Here I'm not taking the transpose of, so I really do not write sigma k given k minus 1 transpose here. Okay? Because this matrix is, we know that it has to be symmetric, and that means that its transpose is itself. Therefore, I don't write those transposes here. So now we're going to define some quantities. Okay? So I can erase this. The first quantity that I'm going to define is going to be just this matrix. So we know that this matrix is nothing but the covariance of yk given y0 k minus 1. But in the Kalman filter literature, or in the literature for this estimation problem, this covariance is given a different name. And that name is usually SK, S something. And I'm defining it as C sigma k given k minus 1, C transpose plus HR H transpose. This is the covariance of the measurement given the previous measurements. Okay? And the second thing that I'm going to define is going to be this quantity. Okay? We know that this quantity multiplies the measurement, and then we add the multiplication into the predicted covariance. Okay? So I'm going to define that quantity as K sub K. Okay? This is SK, this is K sub K. All right? And that quantity is going to be sigma K given K minus 1, C transpose times SK inverse. Okay? This quantity is called the Kalman gain. Gain in the literature. And it is the gain of the measurements when they enter into the state update equation. Okay? So now let me try to write the state update equation using this formula, using these definitions. X at k given k is nothing but x at k given k minus 1 plus the Kalman gain times yk minus y hat k given k minus 1. Okay? You need to remember that y hat k given k minus 1 is nothing but c times the same prediction here. Okay? And what about the covariance update formula? Sigma k given k is equal to sigma k given k minus 1. Then the covariance needs to get smaller. We are subtracting. I have this gain here, like this. So I would have kk, and I would have c times sigma k given k minus 1. Okay? In general, covariances have to be symmetric. And I see that this quantity that I'm subtracting is symmetric. But in this formula, I don't see the symmetricity. Okay? So this kkc sigma k given k minus 1, this really looks like an unsymmetric matrix because of our notation. So that is why sometimes this is written as follows. Sigma k given k minus 1 minus kk. And I would have here s times sk inverse. Okay? C sigma k given k minus 1. So I just add sk times sk inverse here. It's an identity matrix. It changes nothing. But as soon as I make that addition, we see that this is Kalman gain transpose. Okay? So I can modify my covariance update formula as follows. This is equal to sigma k given k minus 1 minus kk sk kk transpose. Okay? So now this really looks like a symmetric matrix, which is nice for us. So I would have sigma k given k update formula is given like this, and this is my state update formula. So now I have to talk about some more of these quantities. So here, in the state update formula, we are taking the prediction and we are multiplying the measurement minus its prediction with a gain and adding it to the prediction. This is the correction that we are doing. This is my erroneous prediction, and we are correcting that erroneous sorry. So we are correcting this erroneous prediction using this measurement, and the amount of that correction depends on the Kalman gain. Kalman gain adjusts how much correction we apply onto the prediction here, which contains errors here. Okay, so but here we are actually correcting this prediction using this difference, this yk minus yk given k minus 1. Okay, this quantity has a specific name in the literature, so we call this quantity as the innovation. Okay, this is again the same name that we used before. Why is that? Because this is nothing but yk minus expected value of yk given y0 k minus 1. Okay, so we call this as innovation at time k, but sometimes if you would like to separate this from the state innovation that we have seen in the past, this is called sometimes measurement innovation. Okay? And this measurement innovation represents the new part, novel part in the measurement yk that is not contained in the previous measurements. Okay? This represents the novel part or the new part in the measurement yk that is not present in the measurements in the past. Okay? That is why it's called innovation. So this sk, we know that sk is nothing but this. Sk is equal to the covariance of yk given y0 k minus 1. Okay? Sk is nothing but the covariance of the measurement. But the interesting thing is that it is also the covariance of the innovation as well. Okay? Y hat k given k minus 1. Okay? The mean is a deterministic quantity. Okay? So if I have the variance of the random variable x is always equal to the variance of the random variable x plus 1, or this is equal to the variance of random variable x plus 3. When you have a random variable, you can add any deterministic constant to that random variable, and the variance of those two random variables would always be the same. Why is that? Because when we are calculating the variance, we are always subtracting the mean. Okay? Mean of x is x bar, mean of x plus 1 is x bar plus 1. So when I try to calculate the variance, here I'm subtracting x bar, here I need to subtract x bar plus 1, which is going to cancel this 1. Okay? So I can actually add a random variable or a random vector, any deterministic constant, and the covariance of it would still remain the same. Okay? So here, what I am doing is that I am subtracting yk, it is conditional mean, given y0 k minus 1. And this conditional mean is a deterministic random variable, given y0 k minus 1. Given the previous measurements, y hat k given k minus 1 is a deterministic random variable, a deterministic quantity. Okay? So that means that I can subtract any deterministic quantity from it. So the covariance of yk is at the same time covariance of yk minus y hat k given k minus 1 given y0 k minus 1. If this conditioning wasn't here, then the covariances might not be the same. But here, because this given conditioning, I have this one, and this y hat is deterministic with respect to this given condition. But that is nothing but covariance of innovation k given y0 k minus 1. Okay? So that is why sometimes this sk, which is the predicted measurement covariance, so this sk is sometimes called innovation covariance, or measurement innovation covariance. Okay? So what does that mean? That means that this innovation nu k is actually distributed, given y0 k minus 1, is actually distributed with zero mean. I have nu k here, zero mean and the covariance sk. Or I can write the distribution of yk given y0 k minus 1. It is distributed as yk, y hat k given k minus 1, and sk. Okay? So this is the distribution of yk given all of the previous measurements. So this is the predicted measurement distribution. Okay? Actually, when we try to see when we look back onto the properties, when we look at the properties of the Kalman filter, we're going to see that innovation process, nu k, is going to be an independent process. Okay? So these given conditions, they won't mean anything. So the distribution, the unconditional distribution of the innovation is just going to be this one. Actually, we know that innovation, this is yk is a Gaussian process. As a result, its innovation process should be an independent process. We have seen this. For any Gaussian process, when we calculate the innovation like this, that has to be an independent process. Meaning that this new k is going to be independent of y0 k minus 1. So as a result, the unconditional distribution of the innovation process is just going to be this one. All right? So that actually completes the measurement update. And now the only thing remaining is our time update. Okay? In time update, I won't need these formulas. I need to erase this. So now let us go into time update. In time update, this is the formula. Okay? So let me write the Gaussian on the left. Normal xk plus 1, and I would have x at k plus 1 given k, sigma k plus 1 given k, is equal to, I have an integral. Now I have the one-step transition distribution here, okay? I need to put it into the integral here. So what is the one-step transition distribution for this system? I need to use the state model, and we have found it in the past. It's nothing but normal xk plus 1, axk plus buk, and the covariance of it is going to be gqg transpose. Okay? This is the one-step transition state distribution. And I have here normal xk, x at k given k, and sigma k given k, and the integral dxk. So here again, one method is to expand this normal distribution, and then make algebraic manipulations and take this integral and calculate this mean and the covariance in terms of this mean and the covariance, and here A, B, and the input. Okay? But here we are not again going to follow that approach. Okay? I will again try to directly calculate the predicted mean and the predicted covariance. And we are going to end up with very similar formulas that we have to what we have found in the past. So now what do we have to do? I need to calculate this mean, x at k plus 1 given k. This is defined as expected value of xk plus 1 given y0k. This is the definition of this mean. And I need to calculate it in terms of this mean and the covariance and the prediction parameters. So I have here xk plus 1, and I know that xk plus 1 formula is this one. Okay? That is equal to expected value axk plus buk plus gwk given y0k. Okay? Distribute the expectation into linear combination here. A expectation xk given y0k plus B expectation uk given y0k plus G expectation wk given y0k. Let us first handle the easier terms. I know what this quantity would be. I know that it is this mean here. Okay? So this is A, x at, so maybe I shouldn't write the next line just now, for now. So here this is x at k given k. And let us go to the second easier term. So this is going to be y0k really WK is independent with everything in the past and in the current. Okay, so this given condition does not mean anything for the randomness of WK. Okay, that means that this is equal to expected value of WK, and that means that this is equal to 0. So this term is in the overall equal to 0. Okay. And here comes the most problematic part here, this expectation. Why might that be problematic? Because UK might be random. It might be coming from the feedback rule here, okay? So here, let us consider this expectation here. Expected value UK given Y0K. If UK is deterministic, there are two possibilities. UK is deterministic, open loop control, or UK is random, closed loop control. Okay? When UK is deterministic, given condition doesn't mean anything. Okay? So this is going to be equal to UK if UK is deterministic. Okay? What about the other case? UK is GK Y0K. I know that UK is a function, a known function of Y0K. Okay? So this is equal to GK of Y0K given Y0K. But given Y0K, this thing is again deterministic. Okay? So this would get out directly of the expectation. GK Y0K. But this is UK. Okay? So really it doesn't matter. Expected value of UK, even though we apply open loop control or closed loop control, it doesn't matter. This expectation is always UK. Okay? So then I can actually write x at k plus 1 given k. Let us write what we have found. A times x at k given k. Okay, and I have b plus b times UK. This is the state update formula. Okay, so that is the state time update formula. Now we're ready for calculating the predicted covariance. So sigma k plus 1 given k given, sorry, sigma k plus 1 given k. So let us calculate that one. Sigma k plus 1 given k, this is by definition covariance of xk plus 1 given y0k. Alright? And this is equal to expected value of xk plus 1 minus x at k plus 1 given k times the same thing transposed with the given condition y0k. Okay? Now let me calculate this difference. Xk plus 1 minus x at k plus 1 given k is xk plus 1 is given there, axk plus buk plus gwk minus, I need to subtract this mean here. It is a times x at k plus 1 given k minus buk. So we see that these buks are canceling here. So whatever covariance I'm going to find is going to be independent of uk. It's not going to depend on the input. And I can here take a parenthesis, a xk minus x at k plus 1 given k plus gwk. And then I need to take the covariance of this thing. But we have done something very similar in the case of the measurement update. Let us write this. Sigma k plus 1 given k is equal to expected value of this thing, a xk minus, sorry, this is xk plus 1. No, I am not making any sense here. Yes, I have found my mistake here. This is going to be x at k given k. And as a result, in this parenthesis, there has to be a less stupid term, xk minus x at k given k, given like this, okay? So I would have this k given k plus gwk, and I would have the same term given y0 k. So now when you expand this outer product here, you would get A times this term transpose times A transpose. So the expectation is going to get inside. So I would have A and A transpose on the left and on the right, and expected value of this term times its transpose given y0k is going to be the matrix sigma k given k, and I would have A transpose due to that term getting outside. And then the cross terms are going to be equal to 0. Why is that? Because wk is independent of y0k, and it's independent of xk minus x at k given k. That means that that expectation can be separated into the multiplication of expectations, and those expectations will be equal to 0. Okay? So the next term is going to be this term times its transpose expected value. In that case, the conditioning doesn't mean anything, so the result is going to be GQ, G transpose. Okay? So our covariance update formula is just going to be this. Sigma k plus 1 given k is equal to, I have A times sigma k given k, A transpose plus GQ, G transpose. So now what is happening in this covariance formula? Remember, the time update is about the propagation of the state in time, okay? And we know that that prediction cannot be exact because of the process noise, which is unknown, okay? So this first term in the covariance update formula is the transformation of the uncertainty in the current state. We are trying to predict xk plus 1 from xk, okay? So we are trying to predict in this covariance update formula the uncertainty of xk plus 1 from xk, okay? So the first thing that we do is to pass the uncertainty of xk from the matrix multiplication A. The first term represents that, okay? So this is the transformation of xk, the uncertainty of xk from the transformation A times xk, okay? This is the uncertainty coming from the current state transformed through this linear transformation AXK. This term, as we saw, doesn't cause any uncertainty increase or decrease, okay? Because this term is exact given all of the past and the current measurements, okay? So this term does not bring us any additional uncertainty, but because we don't know this process noise term here, that causes an increase in uncertainty. This plus sign means that we are increasing the transformed current state uncertainty with GQG transpose. So this uncertainty increase, this covariance increase is coming from this process noise term. Okay? Because we don't know process noise, when we predict the future, we need to increase the current uncertainty a little bit to take the effect of that uncertainness of the process noise. All right? So in measurement update, covariance decreases. In prediction update, covariance decreases. Sorry, I'm starting again. So we start from an initial covariance, okay? In the measurement update, the covariance decreases, okay? Because we get new information, covariance becomes smaller. And in the prediction update, it becomes larger, okay? Because of the process noise. So this type of iteration would continue in the Kalman filter, okay? Of course, depending on the noise terms, we might have something like this as well. Okay, so this process noise covariance might be quite large. So in the prediction, the increase in the covariance might be much larger than the decrease of the measurement update. Okay, so we would get updates like this as well. All right. So you see that I'm drawing these curves like a sawtooth, and they are not diverging away, or they are not going towards zero. Okay? Sometimes those things can happen as well. Sometimes a Kalman filter sometimes the covariance of Kalman filter might diverge, and that is related to the problem of estimatability of the state. Or in control theory, we call it observability. Okay? So if your system does not have observability, we're going to see this in one of the next lectures. If you don't have a concept called observability on your state space systems, these covariances are not behaving this well. They're going to behave violently, and they might diverge to infinity. So here, as the last thing that I would do in this lecture, I will summarize what we have done in this lecture. So we know that we start our prediction x at 0 given -1 from x bar 0, the initial state mean, and sigma 0 given -1. We started with we initiated with the initial state covariance. Okay. Then as we start collecting measurements, we start for k equals to from 0 up to n. I can continue until a final time. We are doing the following. The first thing that I have to do is to calculate the measurement prediction. Y k given k minus 1 is c x at k given k minus 1. And then I calculate the innovation covariance. Sk is c sigma k given k minus 1 c transpose plus hr h transpose. Okay? Look at the innovation covariance. Innovation covariance is also composed of two terms. This is the uncertainty in the state. This is the uncertainty of the measurement noise. So when you try to predict the state, there are two factors. The first factor is the uncertainty in your state estimate. You don't know the state exactly when you try to predict the state. Okay? That is why this first term comes. The uncertainty in the measurement, when you try to predict it, is caused by two terms. First, the uncertainty in the state. The second thing that you don't know is the measurement noise. Okay? And the second term represents the uncertainty of the measurement noise. So I have the innovation covariance. Then I'm ready to calculate the Kalman gain. Okay, k is sigma k given k minus 1. And I have C transpose that and SK inverse. So if your measurement covariance, if your R is very, very large, if you have a terrible measurement noise, then SK becomes very large and your Kalman gain becomes very, very small. That means that the filter thinks that the measurements are very, very uncertain, so that it really shouldn't contaminate its estimates by including the measurements into the estimates with a large gain. Okay? So if the measurement noise covariance, if it is very large, Kalman gain becomes very, very small. Meaning that your filter would like to include the information of the measurements with very, very small gain, so that it doesn't incorporate noise into its estimates. Okay? So we have calculated the Kalman gain, and the next step is to calculate the estimate. X at k given k is x at k given k minus 1 plus Kalman gain times the innovation. We subtract from the measurement all the information that we already have from from the previous measurements. So this is the new measurement. This is the information that we can already predict using the previous measurements. So we are subtracting that old part from the current measurement, and we get the new information. We get the innovation from the measurements, and we add it into, we correct our prediction using that innovation only. Okay? And covariance update is sigma k given k minus 1 minus, I would have here kk, sk, and kk transpose. And then what I have to do is to predict the next time step. Okay? So we see that the covariance, predicted covariance is reduced by the addition of this input here, by the addition of this measurement into the picture. So we have covariance decrease here. And then the next thing is to predict the next state. xk plus 1 given k is going to be equal to a times x set k given k, that formula, plus buk. The input enters into the picture, and then we predict the uncertainty of the next state. I have xk plus sigma k plus 1 given k is a times sigma k given k, a transpose, transformed uncertainty in xk, plus the uncertainty of the measurement process noise, gq, g transpose. Okay, so I can write here end of 4. Okay, and that completes our algorithm. So we see that we need to use these measurements to correct our estimates, and we see the covariance decrease and increase in both parts. We are hoping that we have something called observability, so that the covariances do not diverge indefinitely, and we get this algorithm. So this algorithm is called Kalman filter. Okay? And you see that it contains two parts, state update parts and the covariance update parts. In the next lecture, we're going to start investigating the properties of this algorithm. For example, we're going to see that the innovation sequence is going to be an independent sequence. So in the 1960s, when Kalman first came up with this filter, no one believed him. Okay, so he couldn't publish his studies in standard journals, electrical engineering journals. So he needed to go into mechanical engineering journals to publish his research. But then in 10 years or something, the Kalman filter was used in the space program of United States. Okay, and at that time, of course, the computational powers were really low, so that probably they couldn't implement all of this filter. But we are going to talk about the steady state version of this filter. They could possibly implement the steady state version of this filter. And we are going to see that this algorithm calculates us the minimum mean square error optimal estimates for the state. We're going to be talking about those optimality property of the Kalman filter also in the next lecture. But that is all for this one. Thank you very much for watching. Bye.